All right, so we've explained how the voltaic cell works. We have a pretty good understanding of that copper zinc cell. That's a lot of drawing, that's a lot of artistry. I don't have that ability. I know a few of you guys do, and I'm envious. But for me to draw a cell like that pretty picture that you guys just saw wouldn't work so well for me. So we do have what's known as a cell notation. In the cell notation, we take a look at what is happening in our entities method and try and boil it down to just what the entities are. If we take a look at what was happening to zinc, we know that zinc was being oxidized. And if you take a look at the movement left to right as you read this, you started with elemental zinc and you finished with zinc 2+. The phase boundary is just showing that you've gone from solid to aqueous state. And so this half cell here does have to be the anode. Why? Because of oxidation. We can see that as we look at the elements of that half reaction. The electrons aren't included here because they would have been balanced in your redox reaction. So we're just trying to look at what are the entities. Copper 2+ was your SOA. Oops, I guess I could add that. There's your SRA. Here's your SOA. All right, and you can see that the SOA would want to undergo reduction and therefore turn into elemental copper. Remember that we do reduce to pure metals, and so this half cell must be the cathode. Why? Because we can see evidence of reduction here. The two half cells are completely separated. There's your porous boundary, or the salt bridge, shown by two lines. Okay, so that is the shortcut way that we could draw these things out. It's really just the entities that you see involved in your two half reactions. One for the oxidation, one for the reduction. It's not always anode and cathode when we write these, but we could test for greater understanding just by switching them around. Okay, electrons don't have to flow from left to right on the page. We can also ask you, although I don't really know how I'm going to do that as we go through this in the Learn from Home method, but you should be able to draw and label a voltaic cell. There's lots of different numerical style response questions in which we can test a drawing and your understanding of that one. All right, when we draw these, we usually draw it with the anode on the left, but that is not absolute, okay? So let's take a look at a couple of examples. I have two examples here for you. What would we get out of a lead magnesium battery, and what would we get out of a very expensive copper silver battery? For the lead magnesium, that one is fully solved for us on the next page. It is a guided example so that you have one in your notes in addition to the many that are in the textbook. So flip the page, and if we were to take a look at lead magnesium, okay, with that one, you can see that we have, if we were looking at lead magnesium, we would have lead and magnesium. We're trying to exchange electrons between these guys, so we would also have the lead and magnesium ions. Water, of course, will also be there because we have to make these ionic solutions. So this one's a little bit simplified. Whatever salt bridge is there is just a source of cations and anions, so it doesn't really matter which ones they are so long as they don't participate in the reaction. If we look at this list, your SRA is magnesium, therefore it's getting oxidized. Lead 2+ is your SOA. You can confirm these on your reduction data table if you wish, but take some time to look at that. Reduction then is the gaining of electrons. Remember, reduction always involves the SOA, and therefore, in this case, will be our cathode in the cell that we are making. Oxidation is of the SRA, and therefore will be the anode. We can go one step further. Remember, the anode in a voltaic cell will be negative, so if you wanted to add that, and the cathode will be positive. There's no real reasons for this. We just wanted something to show the opposites, and labeling them this way does kind of make sense why they will flee the anode and move towards the cathode, but they're not actually charged. When you look at this reaction here, you can see that it is spontaneous. We do need spontaneity to make a good battery. If a battery doesn't supply electrons, then it's going to likely take them. All right, so that's charging a battery. That's lessons down the road. Here's our notation. All right, you can see that magnesium was our SRA. It got oxidized to Mg2+. Therefore, this half here is our anode. There's your porous boundary. You need something in between these two half cells to keep them separated so that we can access those electrons. And then you can see lead 2 plus was reduced to solid lead. So there's your cathode. And that's your like two half cells. And of course, there's your SOA. A pretty picture of it, you can start to see all of those various parts shown again. There's your magnesium SRA. The electrons which are negative are fleeing from the anode. They're being produced there, moving away towards the cathode. But the cathode is referencing this half cell, or in particular, the site at which this occurs. And so you can see your SOA here is the lead 2 plus. So the electrons move this way and into that particular solution. In my salt bridge, notice that your lead 2 plus would, of course, start to build up mass on this particular electrode, so you're going to lose 2 pluses. All right, so I need cations migrating towards the cathode side to maintain neutrality. I'm going to be producing an awful lot more magnesium 2 plus as magnesium loses electrons and forms this ion. And therefore I need anions migrating this way. So be mindful of which is going which way out of your salt bridge. From there, the last things we need to add to this diagram, remember that in your voltaic cells, your anode is the source of electrons, so it was identified as the negative electrode. Your cathode then is the opposite and the positive electrode. All right, so that's just taking you through another guided example with me doing a lot of talking. What I want you guys to do is try, before you get into the next lesson here, try the copper-silver cell. Remember, you begin with your entities, do all of your SOA, SRA work, build your redox reaction, and identify the two half reactions clearly, and then identify what would have to be cathode and anode. From there, I would like you guys to show the net redox, show that cell notation, and show a pretty picture of the cell, at least as pretty as you can make it. Okay, because those are the three ways that we're going to look at these cells. We get to really get into in depth on these ones, so make sure that you can do those three things. All right, do copper-silver before you watch the next video lesson. We'll finish off voltaic cells here with that example and a couple of other small terms. See you in the next one.